All right, I'll begin with a word of prayer. Let me start. Dear Father, we thank you for this day again. I thank you for these students and just ask you to help us use this time wisely just to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So here's the Yule attendance sheet. If you could add a day, preferably today's date to it, that'd be good. Well, here we are. It's October. I guess time flies when you're having fun. So something I keep forgetting to do is to talk about the energy stored in a capacitor. Let's talk about it. So all right, so you got some capacitor, right? And what was the defining equation? C equals what? Q over V, right? I mean, specifically that's VB minus VA, where, you know, this up here has voltage B, down here we got voltage A, right? So it's the voltage drop divided into the charge on the plates is the energy stored in the capacitor. So we can ask the question, like, how much work does it take to move dq from one plate to another, basically? So if you think about that, so imagine starting out, we start out with it uncharged, right? Just sitting there. So the first little bit of work, I mean, kind of a typical bit of work, is equal to the change in voltage times dq. So that's how much work it would take to add a charge dq onto the plates. But the thing is, this is what? That. So we can rewrite this as what? And I guess I should have put a big Q here, consistent with my choice of letters. So we've got what? I think we've got Q dq over C, is that right? Change in V is Q over C, right? Oh, okay, so this is 1 over C times Q dq. So the work, integrate so the energy would be equal to the integral of dW, the amount of work it takes. And that would be, 1 over C times the integral of Q dq, which we can do, right? So you got 1 over 2C times Q squared. And of course, we're assuming that the original charge on the capacitor is 0. So there you go. This is the potential energy stored in the capacitor. We've got Q squared over 2C. Now, of course, we can also write that if we just drop the change in voltage and say Q is equal to CV, right? As is often the case, then this becomes also CV squared over 2C, also known as 1/2 CV squared. There's another popular formula for the energy in a capacitor. Anything else you guys think of here? So that's the formula for with Q, the formula with just V. How about if we do a mix? We could have Q and V involved. So like if you go back to this formula right here, you could write this as 1/2 Q over C times Q, which would be what? One-half QV. So there you go. These are the three popular formulas to calculate the energy in a capacitor. You've either got, I'll write them up here again for the record, potential energy in a capacitor with charge Q at voltage V, 1/2 twice the capacitance Q squared, which is also 1/2 CV squared, which is incidentally also 1/2 Q times V. Now, the last formula is kind of interesting because you don't see the capacitance in that formula, right? So that's kind of neat. So for example, suppose you have a capacitor which is 3.0 microfarads charged to voltage V equals to, oh, I don't know, 500 volts. Then how much energy is stored? So let's work it out. What we got? Which formula should we use? Well, if we don't want to make ourselves work, I think we should use the CV formula, right? So energy in this case is 1/2 CV squared, which would be 1/2 times 3.0 microfarads times 500 volts squared. See, 500 square that times 3 times 10 to the minus 6 divide. Oh, that's funny. It actually works out to 3/8. 3/8 of a joule. I don't usually like to leave answers like this, you know. So what is that? That's 0.375 joules. There you go. Any questions so far? So another interesting thing to ask about is, like, where is this energy stored, you know? And I think the best answer to that is it's stored in the electric field itself that lies between those plates. So a natural question to ask then is, what's the energy density? Energy density between plates. Of a parallel plate capacitor. So let's review, how did that go? We had, my bad. So you got these plates, right? And, right, they've got, so they got some area A, right? You've got some particular distance between the plates, right? And what did we work out in this situation? We worked out that the capacitance, it was equal to A. We'll assume that it's air gap, and for approximate purposes, we're just going to say epsilon naught, right? That's an approximation. Technically, it's not quite right, but we'll just assume, like, essentially an air gap. And so for an air gap capacitor, the permittivity of free space is a pretty good approximation. So Ca epsilon naught over D was the capacitance, right? That was one thing we knew. Now, ignoring edge effects, what's the volume? I mean, we could just essentially look at the volume involved here is just A times D, right? And a good approximation, the electric field's constant in there, right? Now, if you don't like this, you could imagine a much larger capacitor, and you could imagine that we're just looking at a cube of volume, you know, a part of the volume that's close to the middle of the capacitor, away from the edge effects. If you want to, you could think of it that way. That would make my derivation less suspect. So that's the volume. And what's the energy? Well, we know that the energy, so my question is, what's the energy per volume? That would give me the energy density, right? So the energy, I mean, we got choices. We could use any one of these formulas, right? I guess I'll go with the 1/2 CV squared formula, just because I'm going to make a choice. There it is. And the volume is AD, right? So well, we know the capacitance is A epsilon naught over D. So this is 1/2 A, 1/2 A epsilon naught over D. That's my capacitance. I've got my voltage squared. I'm dividing by AD. Well, you notice something interesting happens already. The area cancels out, doesn't it? So we get what? We get 1/2 epsilon naught V over D squared. But how is the voltage and the electric field related? I mean, so that's a fine formula right there. This is one description of the energy density, right? It's 1/2 epsilon naught times the voltage divided by the distance between the plates squared. Great. But that doesn't give us much insight into sort of larger questions of what is the energy in the electric field, right? So if we want to look at that, remember how the electric field is related to voltage? Voltage is equal to electric field times the distance, right? If I'm just talking about magnitude. So, so that means that the voltage divided by D is what? It's the magnitude of the electric field. It's E, right? So I can rewrite this as 1/2 epsilon naught E squared. What's interesting, and I think far from obvious, at least as far as I can cipher, is that this is a general truth. So the energy per volume, and energy in electric field per volume is equal to 1/2 epsilon naught E squared. So I've shown you that this pattern holds for a capacitor, and I'm just begging your trust that this actually continues to be true outside the scope of this example. I don't have a good proof for you for that today. I got distracted with students asking me stuff in the office hours. I was trying to find it. I haven't found it yet. I haven't found a proof I found like convincing and plausible for this class, but that is in fact true. If there's a magnetic field, whatever that is, that also comes into play. But there's energy in the electric and magnetic fields. So, like that. Now, a natural question to ask then is to go back to other examples you've done and say, okay, well then what's the energy, for example, in the Coulomb field? What would happen if we calculated that? Could we figure that out? I'm just trying this right now with you guys. Let's see what happens. So, example 2. What's the energy in the Coulomb field? So we'll limit our scope. We'll say for r greater than or equal to some fixed r, right? So we know something funny goes on at the origin for the Coulomb field, right? But let's suppose we just look at the electric field outside of there. How much energy is there in the Coulomb field? It's a fun thing to try to calculate, see what happens. I hope this isn't calculus we can't do in here, but if it is, I'll help you. So the electric field is, as you guys know, kq over r squared, right? That's the magnitude of the electric field anyway. So what's the square of the magnitude? K squared q squared over r to the 4th, right? So the energy And I need another symbol for energy other than E, right? So I'm just going to write it out. Energy. Oh, man. Great. Per volume, dV, is K squared Q squared over, well, I'm missing my epsilon naught. Epsilon naught K squared Q squared divided by 2r to the fourth. I'll get out of the way here. So you guys are in Calc 3, supposedly. And so you know what the volume is for the spherical coordinate system. What is it? I don't know if you guys knew or not. R squared, I want to say sine phi, dr, d phi, d theta, I think. Maybe. Where phi ranges from 0 to pi. Theta ranges from 0 to 2 pi. So to get the energy, total energy, I should just integrate from r to infinity of, you know, epsilon naught K squared Q squared divided by 2, and I've got an r to the fourth there, and then I'm going to multiply that by r squared sine phi dr, d phi d theta. I guess if I was smarter, I would have found a way around this triple integral, but oh well, here it is. 0 to pi, 0 to 2 pi. You guys doing integrals yet in Calc 3? Almost. Okay. Well, this will happen soon enough, although you're not going to do improper integrals unless your professor doesn't know what's good for him. I mean, I don't. And I'm crazy enough. So the long story short of it is this. Let me just get through the details here. I don't want to waste too much class time on this. So this guy and this guy and this guy, they don't interact at all with the r business. They just go to this integral over here. And that all amounts to giving you a 4 pi. So you get a 4 pi epsilon naught K squared Q squared divided by 2. And then you're up against the integral from r to infinity. It looks like we've got a dr over, I guess, r squared, yeah? If I didn't make a mistake. See the r squared and the r to the fourth, they cancel. What's the integral of 1 over r squared? Negative 1 over r, right? Yeah, so we've got 4 pi epsilon naught K squared Q squared divided by 2 times, you know, minus 1 over infinity. Don't tell the other math professors I did this, plus 1 over r. What's 1 over infinity? 0, right? Yeah. Don't do that in your Calc 3 class. There's a limit, you know. Okay, hey, what do you know? So apparently the energy in the electric field outside the Coulomb, outside the radius r, it's finite. It's just this, you know, 4 pi. I mean, we could rewrite that. The 4 pi epsilon and the k cancel, right? So we really just get 1/2 kq squared. Because this 4 pi epsilon naught times k is 1. So these cancel and just leave me a k. I just get kq squared over 2 times, well, 1 over r. And it's not too bad. So there you go. That's the energy in Coulomb field for r greater than or equal to r. What do you guys think? So the further you get away from the charge, like the less energy there is out there, right? You see that? Like if I was to go further out, there'd be less energy in the field further away from the charge. Does that make sense? I think intuitively that makes sense, doesn't it? Right? So let me ask a dangerous question. What's the total energy in the Coulomb field? And so that's, this one. E is kq over r squared, right? That's the magnitude. Same calculation, right? We just have to let r go to what? Big R go to what? We either take the limit as big R goes to what? You don't know? Nobody knows? Infinity? No. No, 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 no. I need to think about the limit as big R goes to 0 from the right. What's the limit as big R goes to 0 from the right of 1/2 kq squared times 1 over r? What happens to 1 over r as r goes to 0 from the right? Infinity. Infinity. This is the famous problem of the infinite self-energy of the electron. What does this mean? It means something's wrong in how we're looking at things. What is that? I have no idea. 0 doesn't exist. I'm pretty sure 0 exists. I mean, I give partial credit, so that wasn't a test score, but, it does exist. All right. I mean, if the electron had some sort of finite extent, for example, if it wasn't actually point-like, then maybe we get around this, right? Because you don't actually take the limit, you just stop at some finite radius, then the infinity goes away. It's just a huge but manageable number. But this is something that theorists struggle with understanding, because it does seem unphysical that the total energy of the Coulomb field should be infinite. It's a finite charge. Why should it have an infinite energy? In relativity, when we study like the self-energy, the rest energy of a mass, we don't have infinite energy. We've got something like mc squared. That's not, doesn't blow up there. It doesn't seem to blow up other places. What's the deal with this? I don't have an answer to this. I'm telling you, this is something people struggle with. So, is this unsettling? I mean, perhaps. But there it is. Let's talk more about circuits, unless you guys have a question. I have posted, oh man. I posted the recommended homework for chapters 23, 24, 25. Am I missing a chapter?
And 26.
And 26. Yeah, and 26. So they're all there. They're posted. I'll try to chip away more of those in the problem session Friday, and maybe even in class Friday. So they're there for you. I also posted the solution to mission 3 just a little bit ago, so that's there. Man, that line charge problem, the coaxial line charge problem, that was kind of a tough problem. And some of those other problems, like why did I give you a whole page? I don't know. Like, this is very silly, but sorry about that. Excuse me. So example 3. Suppose you've got 20 volt battery here, all right, and we've got a resistor, like so. And then we've got a switch over here. All right, and then we've got another resistor. So, and I'll make them both 10K ohm. So my question for part A is, what's the power developed? We call this R1 in R1 before switch closed. And part B, what's the power developed in R1 after switch is closed? All right. I haven't had enough questions in here about power yet, so let's do some. Now, from a circuits perspective, this is pretty simple, right? You guys tell me, what's the story for part A? What's the voltage? What's the current? 20 volts. So we get, so the current is simply 20 volts divided by 10 kilo ohms. And you just told me that that is 2 milliamps. I believe it. So what's the power? Power is equal to, we could do I squared R. If I do that, I have 2 milliamps. I square that. I multiply by 10K ohms. That gives me 40 milliwatts, right? 40 milliwatts. Now that's not the only way you could calculate it, right? Alternatively, you could have just done V squared over R, right? You could have done 20 volts squared divided by 10K ohms, and you would also have gotten 40 milliwatts. There are many paths. You could do the current times the voltage, right? Which is probably what was done. Is that what you did? Yeah, that's good. IV is the easiest one. I have managed to put the easiest one last on my list, as is my custom. I have a vested interest in confusing the students. That is my goal. So I stay on point. I honestly don't see any difference between these three formulas. It's hard for me to, So anyway, 40 milliwatts, that's what it is. What happens when I close the switch? The current gets halved. That's a good answer. So if I do that, like this for part B, then this, I can look at it in terms of equivalent resistance, right? That's funny. But it'd still be, does it change? I don't think it changes. But, oh, now I'm confused. Rats. I'm sorry, let me get, it's the same, isn't it? Because it's still at 20 volts.
It's 20 volts ago.
Dang. What's that?
Shouldn't that change? Because the equivalent resistance is going to be half.
Well, yeah, so well, I guess finding the equivalent, we can do the equivalent resistance thing. It's not, who cares, right? You care? I'll accept it. So, by the principle of auto-caring, there's the equivalence resistance. It's 5 kilo ohms, right? Half that thing. And so then that gives us current 20 volts divided by 5 kilo ohms, also known as 4 milliamps. But then the thing is that this divides, right, between R1 and R2, right? And by symmetry, you only have 2 milliamps going through R1 again. So again, we're back to the power through 1 is I1 times the voltage across 1, which was 20 volts, which again gives us 40 milliwatts. Sorry, this is kind of a boring problem, but maybe it's instructive, I guess. Now, if I asked part C, what's the total power delivered by the circuit, then we feel a little bit more like we've done something, right? What's the total power? You know, by, I'll call it E. Well, then we'd have the power from the first resistor plus the power from the second resistor, which would be a total of 80 milliwatts, right? Because, oh man, look at that. That's not good. Look what I just did. Look at that. This is not good. No. Wow, that was special. All right. Goodness gracious. Let us try another example. So if I was less sick today, I'd probably attempt to do the charging the capacitor right now. But I think I'm going to save that for Friday. So we'll do how to charge, how to find the time-dependent charge and current through an RC circuit. We'll do the RC circuit Friday, is what I'm saying. But for now, I'm going to work an RC circuit which doesn't involve time dependence. It involves what's called the steady state. So if I have something like this, example 4, I could do something like, let's see here, we'll put 100 volts here. And let us suppose I have a capacitor and I have another capacitor like that, all right? And suppose I put a resistance R here and a resistance of 3R here, all right? I close that at t equals to 0, just a little bit after time 0. And let's suppose that this is, 10 microfarads, and we'll let this be 20 microfarads. I wonder if I should be careful not to make an impossible circuit. I don't know. Maybe I should do something. I don't trust myself today, guys. But that's not helpful. I guess I could try to find a problem in the book to make sure I'm not doing something forbidden. That'd be good.
Is there a way to tell if it's wrong?
Oh, sure. We'll work out the work out the rules, and then we'll find impossibilities. Like, I'm not saying this is impossible. I'm just. It would comfort me to find a problem in your book which was similar. Well, that's not it. I'm not sure your book has. Well, your book has the good sense to not put a voltage source in these problems. I'm finding RC problems in your book that don't have well, problem 82 maybe kind of is like this. But there's a single, all right. This is for sure fine. We'll go with that. All right, for now. So the question is simply this. After you close the switch and wait a while, right? After you close the switch and wait a while, what's the energy stored in the capacitor? And what's the power developed in the resistors? What's the voltage at A? Got a laundry list of requests here. So I want to know energy stored in the capacitor. I would like to know the power in R, in 3R, right? And I'd also like to know the, what did I say? Oh, the voltage at A. And I'll put the ground down here just to, for the sake of making that make sense. All right, great. So I'm going to tell you guys the, basically the way to think of this is after you close the switch, right? After a while, once this capacitor is fully charged, once the capacitor is fully charged, you're not adding any more charge to it, right? So we're thinking about t going to infinity in this problem. We want to know like the steady state solution. So after a long time, that capacitor is charged, which means that the current in this, here, I is equal to 0 as, t going to infinity. So like for a large time, there's no current going there. So for all intents and purposes, for after a long time, this is equivalent to the problem where you just have a 100-volt battery. Those are hard to find. But a 100-volt battery, say voltage source, those are easier to find. And you've got 4R here, right? I guess I should have told us a value for R. What do you guys want R to make? R to be? Did I hear kilo ohm? How about that? 1 k ohm. It's a pretty typical value. So if I do that, the equivalent resistance here is simply 4 kilo ohms. And so what's the total current? $100 divided by 4 kilo ohms, also known as 25 milliamps. There we go. So, so we can figure out the power, right? So we have I is, 25 milliamps squared times 1 kilo ohm, and that's the I through the R. The I through the R. Listen to me. The power in the, come on, PR, power through the 3R, would, same current, right? They're in series. So 25 milliamps squared times 3 kilo ohms. What do we get? Uh-oh. Oh. 25 times 25, 620, 625, 625 milliwatts, is that right? And then this is 3 times as much. So 1,875 milliwatts. So of course, if you like, you could write this as 0.625 watts, and you could write this as 1.875 watts. If you're wondering if I care if you write one or the other, I really don't. I would give you full credit for either if they're right. Hopefully they're right in my example right now, right? I mean, I hope. What else then? So I guess it actually pays off to find the voltage at A at this point. What would that be? 75 volts, so you do 100 volts, right? Minus the voltage drop here, which would be I times R. So we've got 100 volts minus, what was the current? 25 milliamps times 1 kilo ohm, which is in fact 100 minus 75 volts, which is 25 volts, which is 75 volts. This is an example of what's called a voltage divider, guys. So if I have a net resistance here, and it's just in series, then the percentage of the resistance is the percentage of the voltage dropped. 25% of the resistance, 25% of the voltage dropped. 75% of the resistance, 75% of the voltage dropped. This is not an accident. This is what's called a voltage divider. Now if current can go here, then it's no longer a voltage divider. So it's not a voltage divider if we were to actually consider the time dependence like we will next class. Like next class, we can actually look at what happens when we close the switch, and we'll understand what happens for short times. We'll work that out, all right? Most likely. But for now, we got 75 volts. And so we can figure out then what's the energy stored on the capacitor. Capacitor is also at 75, wait a minute. Yeah, it's at 75 volts, right? Because it's got 75 volts from here to here. That's the voltage on the plates of the capacitor. And so which formula should we use to find energy? Oh, I erased them, didn't I? 1/2 CV squared, all right. 1/2 CV squared. So we've got 1/2 times 20 microfarads times 75 volts. You got to square that thing and see what we get. I get 0.05625 watts. Watts, listen to me, no. Energy is in joules. So if you like, you could write that as 56.25 millijoules, which is how I like to write that. So the key idea here is simply this, guys. If we are asked a question about a circuit that involves capacitors, and we're interested in what happens after a long time after a switch is closed, to understand what happens, we should think of the capacitor like an open circuit. So no current's flowing there because all the charge is already built up. And so like that's all there is to think about. Now I will essentially prove that that's reasonable by doing the calculus on the RC problem Friday. So we'll actually study what it takes to charge a capacitor by applying, a voltage source to it or something like that. And we'll study how the RC circuit works, the time dependence of that and all that. So that's what's coming up Friday. That's it for today because I'm about to start coughing, so I'm going to shut up.